Tip 1a, we're going to talk more about the concept of the derivative, but we're going to start thinking of it more as an actual function. Up to this point, we've thought of the derivative at a point, some particular point a, and we said that's going to be the limit as h approaches 0 of f of a plus h minus f of a divided by h. And so we said that's the derivative, that's the slope of the line tangent to the curve y equals f of x at the point x equals a. What we're going to do is we're going to say, all right, well, let's see if we can make a formula for f prime where we can let a vary. In other words, we're going to let f prime of x be the limit as h approaches 0 of f of x plus h minus f of x divided by h. And so instead of putting a particular number into this limiting formula, we're going to just leave the variable x in there, and that'll give us some formula for the derivative of the function at any point x. And you can see that this is a function. This is a function that we can graph and draw and do all the things we normally can with a function, and it's a function that depends completely on the previous function, the original function f. We can get the derivative f prime of x. Let's look at an example. Let's let f of x equal, say, x squared plus, let's go 2x squared plus 3x. Okay, and what we want to do then is we want to find f prime of x. We want to find a function for the derivative of the original function f. So the function for the derivative. So what we're going to do then is we're going to say that limiting definition f prime of x is going to be the limit as h approaches 0 of f of x plus h minus f of x all divided by h. Well, that's going to be 2 times x plus h quantity cubed plus 3 times the quantity of x plus h minus f of x, which is 2x cubed plus 3x, all divided by h. This should be the limit here as h approaches 0. So it's going to be the limit as h approaches 0 of, let's see, 2 times, when I cube out x plus h, we're going to get, if we do that, is x cubed plus 3x squared h plus 3xh squared plus h cubed. If you multiply x plus h times itself 3 times, plus, let's distribute the 3 through here, that's 3x plus 3h, and distribute the negative through the second function of f of x, so minus a 2x cubed minus a 3x. All that divided by h. Alright, next step we'll do is we'll run the 2 through the first quantity in the numerator. The limit as h approaches 0 of 2x cubed plus 6x squared h plus 6xh squared plus 2h cubed plus 3x plus 3h minus 2x cubed minus 3x, all that divided by h. We should be able to get rid of every term that does not have an h in it. Let's see. Positive 2x cubed, negative 2x cubed. Positive 3x, negative 3x. Everything else has at least one power of h, or h to the first power in it. One factor of h, I should say. So we have the limit as h approaches 0 of 6x squared h, let's see, plus 6xh squared plus 2h cubed plus 3h, all divided by h. Now what's that then equal to? Well, that's the limit as h approaches 0. If I divide each of these terms by h, I get 6x squared plus 6xh plus 2h squared plus 3. So let me come down here. So what do we have at this point? We have that f prime of x is, again, the limit as h approaches 0. Let me just rewrite what I had previously. 6x squared plus 6xh plus 2h squared plus 3. And we can go ahead and put h into our function. This is a polynomial function that's defined at 0. So we can just plug 0 in for h, and we get 6x squared plus 3. And so that is our derivative function. Now what I want to look at is the graphs of these two functions compared to each other. So I'm going to graph the function f of x, which again was 3x squared plus 2x cubed is what it was, 2x cubed plus 3x, and the derivative function, which is 6x squared plus 3. Let's see if we can get an idea of how these graphs relate to each other. So here are the two graphs. The first one is in red. It's the original function 2x cubed plus 3x. That's the function f of x right there. The second one, the derivative f prime of x, which we said was 6x squared plus 3, is this graph right here. Now what I want you to pay attention to is that we can actually get a good idea of what f prime of x looks like based on the graph of f of x. What does f prime of x tell us? It is at any point x the derivative, so it's the slope of the line tangent to the graph at that point. Alright, well, let's think about that. You look at the lines tangent to the graph as we have x in negative territory here. The lines tangent are all positive. The lines tangent are all increasing. We have a positive slope here. That means our derivative is going to be positive. That's why the derivative exists in positive territory here. It's above the x-axis. Now it's decreasing. Why is that? Well, because the lines tangent, the slopes of the lines tangent are getting flatter and flatter. As we move along here and you draw lines tangent to the graph, they're getting flatter and flatter and flatter. So that means that the y values, which are the slopes, the y values of the derivative, which are the slopes of the original function, are decreasing. And it looks like they come down to 3, which tells me that if I were to draw the slope of the line tangent to the curve at x equals 0, I would get a value of 3. Let's check that. Look at our function here. F prime of x is 6x squared. If we take f prime of 0, we get 6 times 0 squared plus 3, which is equal to 3. So the y value, if we draw y equals f prime of x, the y value when x is equal to 0 is 3. And that shows on our graph here. And so that is the least steep that our graph gets. And now what happens after that? Well, the slopes get steeper and steeper and steeper again, so the y values of our derivative start to go up. Alright, so what you want to recognize is that first of all, the original function f of x is always increasing. That means that the slopes of the line tangent are always positive. That means the derivative function's graph is always positive. It's in positive territory above the x-axis. And what else can you see? Well, as x heads from negative values towards 0, the line's tangents start to flatten out. They get to their flattest point when x is equal to 0, and that slope of the line tangent there is 3, which is why the y value here, when x is 0, is 3 of our derivative. And then the slopes start to increase again as the graph gets steeper, so the y values of the derivative function start to go up. Let's look at another example. Let's suppose we were given a function and wanted to draw the derivative based on the graph of that function. Let's suppose we're given this graph here, and the dark blue graph is y equals f of x. And from this graph, we don't know the formula for it, but from this we want to sketch a graph of the function y equals f prime of x. Alright, well here's where we're going to start. First of all, I'm going to find places on my original function where the derivative is 0. How can I find those places? Well, that's easy. That's where the lines tangent to the curve are going to be flat. I have two such places. Here at, if we label these at negative 2, you can see my slope here is 0, so we can see that f prime of negative 2 is 0, and also we'll say positive 2. We can see that the slope here, which is f prime of positive 2, is also 0. So when I graph my derivative function, which I'll do in light blue, the value of the derivative, the y value at negative 2 and 2 is 0. So that means I'm going to cross the x-axis at those 2 points. Okay? Now the y value of my derivative function, let's say for values of x that are less than negative 2. Well, the function is going up, it's increasing, the function's increasing, and so the slopes of the line tangent are going to be positive. So my y values of my derivative are going to be in positive territory, but what's happening to the slopes? Very steep here, and they're getting less and less steep as we come towards x equals negative 2. So the y values are positive, but they're getting less and less positive and coming towards 0 until they get here to negative 2. Now what's happening? Well, now the derivatives are negative, and they're getting more and more negative because the slopes of the line tangent are decreasing. The lines are decreasing, so the slopes are going to be negative. So as we go from x equals negative 2 to say x equals 0 here, the y values are decreasing. And it looks like they're going to get, the lowest that they're going to get is right here at x equals 0. That looks like the most steep in the negative direction they're going to get. And then you can see that the slopes start to flatten out again and start coming back up towards 0. And so my graph of f prime is going to start coming back up towards 2 right here, towards 0 when x is equal to 2. Now what happens to the right of x equals 2? My original function f of x, the slopes of the line tangent start to get positive and start to get more and more positive, increasing. And so my derivative values are going to be positive, so they're going to be above the x-axis, and they're starting to increase in that direction. So there you can see that the graph y equals f prime of x can be drawn based on the original graph of the function y equals f of x. And it's not a perfect graph, but you have an idea of what it's going to look like. Let's take a look at a little program here that illustrates that a little bit better than I can do with my drawing. We have a function y equals f of x, which you can see here. And we have a point on there and a little triangle at that point. That triangle gives us a way to measure the slope of the line tangent, or the derivative. Remember, the slope of this line here that's tangent to it is going to be measured by the change in y values divided by the change in the x values. And so they show you a little triangle here, 0.27 over 0.25. That's pretty close to 1, a little bit bigger than 1. So the derivative at this point here is right about 1. Now, we're also going to be sketching out then the derivative function based on the original function f of x. Well, you can see that the derivative function has a y value at this point right at about 1, because that's what the derivative is equal to. Now you can see as we're going to move this point here to the right, you can see the slope of the line tangent is going to start to decrease and head towards 0. That means the y values on f prime should decrease and head towards 0. Let's look what happens. As we move here, we decrease, and now we're at 0. The derivative is at 0. You can see because the line tangent is flat. If I can get to that point, maybe. Alright, so I'm pretty close here, and the derivative value is at 0. Now we're going to start to head into negative territory because the function's decreasing, so the slopes are going to be negative, and so the y values of f prime are going to be negative. And we can see that happens here as we go down. Now we got about as negative as we're going to get right here. And so now the slopes are starting to come back less negative, come back towards 0, which they'll get to right here, and the y value of f prime will come back to 0. So we have that point there, we're back to 0. And now the function starts to increase, so the y values of the derivative are going to be positive, and they're going to get more and more positive as we move on here. Alright, so you can see what's going to happen. If you watch this process, things you want to remember are that there are places where the derivative is 0. You see right here, the derivative is 0 because the line tangent is going to be flat. Well, we cross the x-axis there for our derivative function. Here's another place where the derivative is 0 because the line tangent is flat. That's where we cross the x-axis. Derivative is 0 up here. We cross the x-axis at that x value. The derivative is 0, a little bit less than 3 of the original function because the line tangent is going to be flat. And a little bit less than 3 is where we cross the x-axis. Wherever the function is increasing, the derivative function is above the x-axis because the derivative is positive. Wherever the function is decreasing, the derivative function is below the x-axis because the derivative function is negative. Let's look at a different function. How about this function here? Well, we look at this one here, we're getting steeper and steeper, and then we get into negative territory. Let's take a look here. The derivative, the slope of the line tangent, is positive, getting more and more positive and increasing. But then if you jump over this line at x equals 0, here the derivative is negative, but starting to level out towards 0. There's actually a discontinuity in our derivative function here, you can see, and that's because this original function is not differentiable at the point x equals 0. We'll talk more about that in a little bit. Let's look at one more function. How about the sine function? What you want to notice is wherever we make a turn here, that's where the derivative is 0, you'll be crossing the x-axis on f prime. Take a look at that. So wherever you make a turn is where the derivative function goes through the x-axis. And you can see that's the derivative function being traced out there. Okay, next thing I want to do is briefly mention some other notations that you're going to see when we talk about the derivative. If we have the function y equals f of x, we can write the derivative lots of different ways. F prime of x is going to be the most common. We can also write it as y prime. We can write it as dy dx. We can write it as df over dx. We can write it as d dx of the function f of x. Sometimes, but rarely, it's written as big D f of x, and sometimes also it's written as d with the little x as a subscript f of x. These all mean the same thing, the derivative function of the original function f of x. In particular, we look at this notation here, dy dx or df dx. This notation is suggestive because remember one of the ways we defined our derivative was the limit as delta x approaches 0 of delta y over delta x. So it's a change in y over the change in x, and so that notation is there to suggest just that very concept. And if we want to do that at a particular point, for example, if we want to take f prime of 2, we could also write that as dy dx at x equals 2 as a notation if we want to take the derivative at a particular point. Okay, last thing I want to talk about in this lecture, in this video, is where a function is not differentiable. So this discussion is on page 162 in your book. And the first thing they talk about is a corner, where a function is not differentiable as a corner. And one of the examples they give you is, you just look at the function f of x equals the absolute value of x. Now we know what that function looks like. It just kind of is a v here that comes down like that, down like that. We have a nice corner here, or a cusp, we could call it, at the point x equals 0. The function is not differentiable at that point when we have a sharp turn like that. Now why is that? Well, what's the slope of the line tangent to the curve to the left of 0? The slope of the line tangent is a -1. All throughout here, for anything over here, f prime of x is equal to -1 if x is less than 0. What about to the right? Well, if we look at the slope of the line tangent to the right, you can see the slope here is going to be +1. So f prime of x is equal to +1 whenever x is greater than 0. Well, the derivative is defined, if you want to take the derivative at 0, the derivative at 0 is only going to exist if the limit of f of x plus h minus f of x all over h, when x is equal to 0, coming from the left and coming from the right is the same. In other words, if you take the limit as x approaches 0 from the right of f of x plus h minus f of x divided by h, what are you going to get? Well, this is just the derivative, and how the derivative changes as we approach it, it's going to be a positive. That's not right what I just said. Let's start over here. Let's take the limit of the function f prime of x as x approaches 0 from the left, f prime of x. Well, the derivative is constant throughout there. It's always a -1. And so the limit as x approaches 0 from the left of the derivative function is going to be -1. But the limit as x approaches 0 from the right of our derivative function, here we have a positive slope here, that's +1. Well, that tells me then that the limit as x approaches 0 of f prime of x does not exist. Why is that? Because for a limit to exist, that means the derivatives coming from the left and the right have to exist. So that means that the derivative, we would say that f of x is not differentiable at x equals a. There's two other cases then when we don't have differentiability. One is a discontinuity, and so anytime a function is not continuous, then it is not differentiable, and that's what we're told in Theorem 4. If you look at Theorem 4 on page 161, it says that if f is differentiable at a, f is continuous at a. So in order for a function to be differentiable at a point, it has to be continuous at that point. And finally, part C, the last place we can have a point on a graph where the function is not differentiable is when we have a vertical tangent. And you can see a picture of that in the book. It would be something along these lines where the slope of the line tangent is actually a vertical line. Well, the slope there is undefined, and so the slope of a vertical line is undefined, and so the derivative, which is the slope of the line tangent, would be undefined as well. So those are three places where a function can fail to be differentiable. And we'll look at some examples and some higher derivatives in the next video.